Thank you for joining us for the 2024 Sure Grid Fellowship. I'm Alex Bennett.
And I'm Erin Clark. The cyber attack on Ukraine's power grid has caused power outages for more than 225,000 consumers in western Ukraine. The outages lasted from 1 hour to up to 6 hours.
A regional electricity distribution company in Ukraine was the first to report the power outages to its consumers. The outages were due to a cyber attack on the company's computer systems and SCADA systems, which stand for Supervisory Control and Data Acquisition.
These are computerized systems that monitor, control, and analyze industrial devices and processes. SCADA systems are made up of hardware and software, and they allow users to collect data from devices remotely.
The attack has been attributed to a Russian attackers group called Sandworm. This is the first publicly acknowledged successful cyber attack on a power grid. These hackers intended to test a remote cyber operation directed against Ukraine's critical energy infrastructure.
The malware or malicious software disconnected electrical substations, causing a blackout. The hackers used the Black Energy 3 malware remotely to compromise information systems of 3 energy distribution companies in Ukraine and temporarily disrupt the electricity supply to consumers.
Yeah, I think a combination of the name of the program is Sure Grid, so in my head it was the electric grid, so I think that kind of bias drew me there, along with, again, the electrical engineering background. I understand a little bit more than I might about a water system, so I think it was a very good choice.
Yeah, and I think we now live in a world where cyber threats are becoming ever more complex, so I think kind of focusing in on the electrical grid is becoming more and more relevant.
Yeah, at the beginning it was a lot of taking in information, reading as much as we could, and now we're sort of focusing in more on the specific grid topology and reading a lot of technical articles about substations. Yeah, but moving forward, our strategy is to really hone, keep honing and not be so broad. Now we have more of a focus, I feel. So me and Abby were on the engineering side, so we've been looking into the power grid for our first use case, and specifically we've been looking at the substations and how they work, the different hardware aspects of it, to figure out sort of how to ensure grid reliability and resiliency.
A circuit breaker is an electrical component that is used to protect an electrical circuit from damage. These devices appear in homes, typically aggregated together in one box in a basement. When there is an overload, too many things are plugged in, requiring too much power, or there is a short circuit. An unintended connection is made in the circuit. For example, don't stick a fork in the outlet. The circuit breaker will trip, opening the circuit and disconnecting the power. In a home, these devices are small, and the circuit can be reconnected to restore power with the flip of a switch. Circuit breakers are also used in the electric grid on a much wider, far-reaching scale. These are high-voltage circuit breakers that are much bigger than the ones in homes, and utilize springs to open the circuit as needed. These large circuit breakers can be observed in action when a home loses power briefly during a thunderstorm, because the extra electricity from lighting will cause the circuit breaker to open briefly to prevent the excess of power from causing damage. In the United States, electricity is generated by converting energy sources like natural gas and wind turbines, then transmitted from power plants to cities and rural areas where it is used. There are 3 stages: generation, transmission, and distribution. Transmission moves electricity at high voltages, and the voltages must be gradually stepped down to lower voltages in order to be used in homes and offices safely. Transmission substations house transformers that transfer power from region to region, and play a critical role in changing the electric voltages to then supply electricity to adjacent distribution substations. Tampering with distribution substations makes it unsafe for power to be distributed to households and businesses. Interfering with transmission and distribution substations can cause blackouts regionally. When thinking about the United States, this is a map of the different substations in our area.
I want to say it was, I know it was California. I want to say it was right outside San Francisco. The town escapes me. Back in the mid 2010s, there was another instance of an attacker, again, shooting at a substation with the intention of just taking it down. In that instance, what caught the attack was actually proximity motion sensors that just when equipment fell off, it tripped one. A security guard looked at a camera and was able to see at that time just kind of sparking and notified authorities to take action. Cameras and motion sensors, gate sensors for physical security on substations are becoming very common, although there are some pushes from the federal level that substations really need to do a little more. Most substations are just protected by a chain link fence and a gate. And that doesn't really offer a lot for them. The minimum the federal government was asking in those instances was, why aren't there so much as sandbags behind the chain fence that would protect from a projectile? So physical security, we us being cybersecurity people, we always talk about cybersecurity, but physical security is very critical in this, because we can have the flashiest, most advanced cybersecurity solution out there, but if one person with a rifle can take out an entire county's power and we're unaware of it, that is a huge problem. And it's one that we saw in that year through the U.S. geographic South, North Carolina, South Carolina, Florida, and throughout the Pacific Northwest, all over the span of about 3 months.
Team 4 is working on a simulation for this use case in Simulink to simulate a real-world generator. Machine and regulator simulation, representing a real-life generator that's connected to a simulated power line, and then a subsystem that includes the load the system is powering and switches representing the circuit breaker. This video is going to go over all blocks used in the simulation and what some of the important parameters are. The power GUI block is just a required block in Simulink to let the simulation run. Starting at the beginning with the synchronous machine block, the PM and VF values are just constants used in electrical power engineering. PM represents the mechanical power of the machine. Taking a look at the parameters, all of them are going to be left at default values. But you can see the machine is at 60 Hz, which is the standard value for electricity in the US. And the VRMS value is at 13.6 kilovolts, which is quite a high voltage. A standard outlet is 120 volts, so this is definitely a value you would see in a high voltage power line in the electric grid. There are a lot of possible outputs to the synchronous machine block. There's the current of each phase, voltage for each phase, the rotor angle that we're concerned about, and the power of the generator. These are all outputted on one bus that just has every output labeled M, and we use the bus selector to pull out the values that we want to be able to see, and then some unit conversions blocks connected to the scopes. Scopes just represent a place where we want to see a graphical representation of whatever the output signal is at that part of the system after the simulation has been run. The line block box just has some resistors and inductors to replicate a more realistic power system. It also has a block that gives a current measurement from a scope block in the main simulation window. The fault timing block sets an output of 1 or 0 based on the value at the time specified in the transition steps. The lab is going to change the timing in a way to control the opening and closing of our simulated circuit breaker. Looking closer at the subsystem, it uses a controlled virtual source block with a calculation to get the voltage amplitude that corresponds with the 13.6 kilovolts VRMS of the machine. These blocks are the simulated representation of an infinite bus, which is an ideal component used in electrical simulations that will maintain a constant voltage regardless of what happens in the rest of the system. The control line is coming from the fault timing block mentioned before, which controls these two switch blocks. When the breaker is closed with a signal of 1, the sine wave will go through the switches and interact with the voltage sources.
that are connected to the generator, to the 3 phases of the generator, and give them an AC voltage. When the control is 0, the constant 0 will go through the switches, and the voltage sources will not have any voltage at all. Because in real life, an open circuit breaker will completely disconnect the load from the sources in the circuit.
Cyber-informed engineering is a cybersecurity principle, but it's more holistic. It makes you look through like the whole engineering process instead of like traditionally like you'd build the computer and then just throw like cybersecurity on top of it with like an antivirus and a firewall. But throughout this process, we're looking at critical infrastructure and how we can integrate cybersecurity into the earlier stages of the process and throughout like the whole thing and the actual physical system itself as opposed to just the computers. For our use case, the main CAE principle we are looking at is consequence-focused design. That is what our lab is about. We are showing that if a circuit breaker is opened, like with the Ukraine use case that we're looking at, where attackers got access to the system and then were able to manipulate the circuit breakers in the system to open them, we are showing that if that happened with the generator, it can not only disconnect the people from power, but it can also cause damage and instability to the generator itself. So you have like both of those consequences. You have like, obviously people need power, things like hospitals need power, but also you want to make sure that like, even if in the case of an attack, you're not losing the system, it's not breaking. Some other consequences we're talking about are secure information architecture. We want to make sure that we are using proper authentication and having good security policies so that only people who should be accessing the system have access to the system and can change the data. So the attackers, like in the Ukraine attack, can't just steal credentials and then have access to the whole system. Like, you want to have things like multi-factor authentication, or maybe like have multiple people controlling critical parts of the system.
So a broad approach to ensuring a secure power grid requires understanding that a perfect technical solution to an engineering problem may not be effectively implemented or scaled to work within an organization's existing culture. Before technical approaches can be leveraged to mitigate the possibility of attack and address the consequences, if an attack is successful, an organization must have security at the forefront of their practices. CIE Principle 12, Organizational Culture, involves ensuring that everyone's behavior aligns with the security goals of the organization. The strongest countermeasure is fostering a strong cybersecurity culture in the leadership and having these values step down throughout the organization. Having a strong cybersecurity culture involves training for all users of the system. Additionally, a specific measure for emphasizing strong values and management is centered in defense in-depth strategies. Thinking internally, a specific area to focus on is privileged access management, otherwise known as PAM, a type of identity management and cyber defense mechanism that plays a critical role in defense in-depth strategies and enabling zero trust. By reducing privileges to the operational processes in the substations to ensure that control of the utility is contained to trusted individuals with high clearances is what PAM primarily focuses on. So by implementing strong security measures at every level of electrical grid operations from the top down, electric grid security will be enhanced. These internal policies, combined with strong overarching regulatory policies like NERC-CIP and the Safety Act, ensures that the external and internal policies cultivate environments in which cyber physical power systems are well protected and secure.